Hi everyone, I'm Minesh and I will talk about beer. So I'll start out with a high-level summary of our work. The problem that we tackle in this work is that DRAM on IEEE complicates reliability studies by obfuscating DRAM error characteristics, and to overcome this problem, our goal in this work is to understand exactly how IEEE obfuscates errors. To achieve this goal, we make two main contributions in this work. First, we introduce beer, which is a new testing methodology that determines a DRAM chip's unique IEEE function, in other words, its parity-check matrix. And second, we introduce beep, which is a new testing methodology that infers raw bit error locations of error-prone cells using only the observed uncorrectable errors. Finally, we evaluate beer in two ways. First, we experimentally demonstrate beer using 80 real LPDDR4 DRAM chips from three major DRAM manufacturers. And second, to complement our experimental studies, we evaluate beer in simulation, where we show beer's correctness and practicality for over 100,000 representative IEEE codes of varying word lengths. Now I'll give an overview of our work in a little more detail. So third-party DRAM users, such as system architects who design error mitigation mechanisms at the system level, test engineers who perform extensive third-party testing and validation, and research scientists who conduct experimental error characterization studies, all need to understand a DRAM chip's reliability characteristics in order to effectively do their work. Now, these characteristics include things like looking at manufacturing variation between different DRAM chips, the location of weak cells within DRAM chip, and so forth as shown on this slide. The way that they determine these properties is by using extensive DRAM testing and error characterization. So given a DRAM chip, they study the observed bit flips when errors occur. However, modern DRAM chips include on-die error correcting codes, or ECC, which are unknown and proprietary, and provide no feedback to the CPU upon error correction. Therefore, on-die ECC obfuscates the errors they are trying to study, and this means that on-die ECC complicates reliability studies by unpredictably obfuscating raw bit errors. Now, to overcome these challenges, our goal in this work is to determine exactly how on-die ECC obfuscates errors, in other words, to determine its parity-check matrix. And in the context of a real DRAM chip, this means that we want to know exactly what happens within the ECC logic, because this would both reveal exactly how on-die ECC scrambles errors and allows us to infer raw bit error locations corresponding to uncorrectable observed errors. And in order to achieve these, we introduced two new testing methodologies, beer and beep. Now let's talk about these methodologies in more detail. So both beer and beep are based on the key idea that disabling DRAM refresh induces data retention errors only within charged cells. And here we illustrate two different states that a single DRAM cell can be in. On the left, the cell's storage capacitor is shown fully charged, and we refer to this as the charged state. On the right, the cell's capacitor is shown as discharged, and we refer to this as a discharged state. Now, when we induce data retention errors, we can cause a charged cell to go to the discharged state, but an already discharged cell will typically not flip to the charged state. And this means that we can selectively induce errors by controlling bit flip directions. Now, using this principle, we developed beer, which is a new three-step testing methodology that first induces uncorrectable data retention errors by disabling DRAM refresh operations, then identifies which uncorrectable errors are and are not possible, and finally solves for the parity-check matrix that's responsible for the observed errors by using a SAT solver. Now let's take a look at each of these steps in more detail. So in the first step, we start with a set of carefully chosen test patterns where only some of the bits are set to the charged state. Next, we disable DRAM refresh to induce uncorrectable data retention errors. And finally, we observe different error patterns for each test pattern across different ECC words throughout the DRAM chip. Now note that these errors only occur in specific bit positions because not all bits are set to the charged state. Next, we identify which uncorrectable errors are and are not possible for each test pattern. And in order to do this, we make a table of the different test patterns, and then we itemize which bits are susceptible to errors and which bits are not. Now this is important because this table will be different for different ECC functions. Finally, we solve for the parity-check matrix. And in order to do so, we input the table of possible errors and the basic properties of a Hamming code as constraints to a SAT solver. And upon evaluating the SAT problem, we get the parity-check matrix that's responsible for the observed error patterns. Now in summary, beer determines the parity-check matrix without hardware support or tools, prior knowledge about on-die ECC, or access to ECC metadata, for example, error syndromes. Finally, we open source beer as a project on GitHub at the link shown on the slide. Now we evaluate beer in two different ways. First, an experimental demonstration using real LPDDR4 DRAM chips from three major DRAM manufacturers, and second, in simulation to show beer's correctness and practicality for various representative on-die ECC codes. Now our experimental results show that different manufacturers appear to use different parity-check matrices, and chips of the same model appear to use identical parity-check matrices. and our simulation results show that Beer works for all simulated test cases and is practical in terms of both runtime and memory usage. Finally, in our paper, we show how knowing the parity check matrix via Beer is useful in practice for designing reliable systems, efficient testing and validation, and performing effective error characterization studies. And if you're interested in these use cases, please look at our paper for more detail. And thank you for listening to my talk.